Okay. I will be speaking about secret sharing schemes, old lower bounds and new upper bounds. Title approved by the committee. The title reflects the fact that basically there wasn't a major or a lot of progress in general lower bounds for secret sharing schemes since '94. And recently there have been dramatic improvements in the upper bound for secret sharing schemes. And unlike the title, I'll also speak about some lower bounds that are new. Okay. So let's start by my lecture plan. As I said, I will start by defining a secret sharing scheme, general secret sharing scheme, not threshold as in previous talks. And I'll give a simple construction. I'll be speaking about lower bounds. Then I'll be speaking about the upper bounds. I'll give a hint about the new upper bounds. And I'll end with one slide of conclusions. So what are secret sharing schemes? Secret sharing schemes were defined by Shamir and Blakely in '79 for threshold case, and by Ito, Saito, and Nishizaki in '87 for the general case. So again, we have a dealer. The dealer holds a secret, and there are n parties. And the dealer applies the functionality to the secret and generates n strings, which we call shares, and gives each share privately to the appropriate party. So P1 gets S1 and so on. And for each secret sharing scheme, for general secret sharing scheme, we have an access structure. An access structure is simply a collection of sets of parties. And we say that the secret sharing scheme realizes an access structure, gamma, if the two following conditions hold. The correctness says that every authorized set, a set in the access structure, can recover the secret S from its shares. And the security says that every unauthorized set, a set not in the access structure, cannot learn anything about the secret from its shares. So this, in this talk, on most of the literature on secret sharing schemes, it's information theoretic security. And we have two seemingly contradicting requirements, correctness and security. For this, to achieve this goal, we have that the dealer has to be a randomized function, so its input is the secret S and a random string R, and it computes the random strings. Okay, so this is the definition of secret sharing schemes. It has many applications in crypto for secure storage, secure multi-party computation, and many more. I won't go into it in this talk. So let's see a general construction for secret sharing scheme. It's one of the two constructions presented in the original paper of Ito, Saito, and Nishizaki. So a necessary condition for an access structure to have a secret sharing, the access structure has to be monotone. If some set can reconstruct the secret, so every superset of that set has enough information to reconstruct the secret. So the necessary condition is that the access structure is monotone, and this is actually a sufficient condition. And to prove that it's sufficient, I'll do it via an example. I'll consider an access structure with 5 parties and 3 minimal authorized sets, so P2 and P4 authorized, P1 and P2, and P1, P3, and P5 are authorized. And for each set, each minimal authorized set, we share the secret S independently. So in this example, the secret will be 1 bit. So for P2 and P4, we choose a random bit R1 and give R1 to P2 and give S exclusive OR with R1 to P4. And we do it independently to P1 and P2. So we choose another random bit and give the random bit to one party and the random bit exclusive OR with S to the other parties. And again, we do it independently for the third set. In this case, we choose 2 random bits and give the exclusive OR of this bit and the secret to the last party. So each authorized set, each set in the access structure, there's a minimal authorized set that is contained in that set, so it can reconstruct the secret. On the other hand, if you take an unauthorized set, For example, P2, P3, and P5, they cannot learn any information about the secret because they miss at least one bit for each sharing. For instance, P2, P3, and P5 miss this bit, so what they see is this uniformly distributed bits, and that is independent of the secret. So this is a general construction. So we know that we have a necessary condition, we have a sufficient condition, so we can end the talk here. Okay. There's only one problem with this scheme. What is the problem with the scheme? The problem is that the length of the shares. So we show that every monotone access structure can be realized, but the share size is 2 to the n. For each party, the size of the share is the number of sets that contain that party, and it can be exponential. So the size of the share in this scheme is exponential. Since in production of secret sharing schemes, there have been many constructions of secret sharing schemes. We can construct secret sharing schemes from monotone formulas. We can construct it from monotone span programs. And there are many more constructions. So if a function has a small monotone formula or monotone span program, then it can be realized efficiently by secret sharing scheme. But still, in these constructions, for the worst access structure, the size of the share is 2 to the n. So until recently, this was the best known secret sharing scheme. Lately, there have been improvement in this, a dramatic improvement in the share size. It starts with the work of Tianren and Vinod that shows it can be, there's a construction to 2 to the c times n, where c is smaller than 1. And there's been a sequence of works improving this constant. And the current best record is 2 to the power of 0.64 times n in unpublished yet paper of Benny Applebaum and Oded Nir. And all these constructions are from conditional disclosure of secrets. Since this is the upper bound, I won't mention it in the talk. In the last part of the talk, I will get into some details about it. So one of my plans for the talk is to start saying that lower bound is upper bound is an impossibility result for lower bound, so I'll speak about the upper bound, but I decided to mention some things about the lower bounds. So this is what is known for the lower bound. So I finished my first part of the talk. Let's show what is known for lower bound. So the best lower bound for general secret sharing schemes is from 1994 by Tsirmas. What he shows that there exists an access structure that for every finite set of secrets, the total share size of the scheme is n squared over log n times the size of the secret. So n is the number of parties. So the upper bound is basically quadratic in n. And this is the best lower bound. To compare, the best upper bound is exponential in n. And there's a large gap. And there's no major progress in general lower bound for secret sharing schemes since 94. The n squared over log n wasn't improved. Even removing the log n factor wasn't done since then. Modest question, prove an n squared lower bound, not known since then. What I'll do next is discuss some lower bounds for specific cases. So first I want to mention, okay, before that I'll, going into that, so the question is, are there efficient secret sharing schemes? And I'm giving two conjectures. I put a question mark against the conjecture because I don't know if I believe it. I probably don't believe it nowadays. So there's two conjectures. The first one is that there exists an access structure that requires shares of size 2 to the omega of n times the length of the secret for every size of secrets. So this is one conjecture. A weaker conjecture is that this only holds for one bit secret. So a weaker conjecture is that there exist access structures that require shares of size 2 to the omega of n for sharing a one bit secret. And the second conjecture implies the first. The first conjecture implies the second conjecture, but it's possible that the second conjecture holds that sharing one bit requires exponential in n, but sharing longer secrets requires exponential length. We have some evidence for that from a work of Benny and others. Some of parts of it will be mentioned in the next talk, showing that for some class of secret sharing schemes, sharing long secrets can be done much more efficiently than sharing one bit secret. As I said, these are conjectures. In some papers they say it's Beimel conjecture. I never mentioned it as a conjecture. I only said it's an open problem. I was coward. But I did believe in conjectures. Nowadays, I don't know if I believe the conjecture or it can be, everything is possible. So, as I said, the question is disprove these conjectures, and proving these conjectures even for implicit access structure, showing that the existing access structure that requires long shares is open. So even to prove that something exists is not known, if the conjectures are true. Okay, this is the general case. I will prove two restricted cases. One is not a law, but it's limitations of the new constructions. So as I said, there are a series of works that showing that the construction with 2 to the c times n, where c is smaller than 1. And I want to show some limitation for what this technique can achieve. This was communicated to me by Tony Pitassi. To prove the limitations, I will have to recall the notion of a slice function. A slice function is a function from 0 to 1 to the n to 0 to 1, such that there exists a k, such that all inputs of weight more than k that have more than k ones in the input are 1. All input of weight less than k are 0, and the input of weight k can be either 1 or 0. So let's see a simple example. In this case, we'll show a slice function for k equal 2. So all inputs of weight at least greater than 2 of weight 3 is 1. All inputs of weight less than 2 of weight 0 or 1 are 0. And for input of size 2, it can be either 0 or 1. So in this example, 1, 0, 1 is 0, while the other two inputs of weight 2 are 1. So this is a slice function. And why do I care about these? So all the new constructions with size smaller than 2 to the n use the monotone formula to realize the secret sharing scheme. And the gates in the monotone formula are threshold gates, AND gates, or OR gates. Actually, AND and OR are simple threshold gates. And these are the simplest examples of a slice function. And they also use CDS gates. And CDS gate, it can be shown the CDS gates also are, what did I do? Okay. And it can be shown that CDS gates are also slice functions. They only realize slice functions. So, and the size of the shares in these schemes is proportional to the size of the monotone formula. So the question is, what is the size of the monotone formula with slice functions as gates for the worst function? And it turns out that the size of these circuits, of this formula has to be large. So what we know, without going into too much details, we know that every formula with slice functions of size, where the size of the formula is S, can be simulated by a monotone what is known by monotone wheel formula with a fan-in 2 of size order of S. So in a monotone wheel formula, the inputs are binary, but the wires can carry any value. And each gate has fan-in 2 and computes a monotone formula over the wheels. So if we have a slice function, we can compute it by such gates. So so every wheel, so slice functions imply a size with a multiplicative factor, stronger formula, and for such formula, there's an exponential lower bound. From the 90s, we know that there exists a monotone formula F, such that every monotone ring formula for F has size 2 to the omega of n to the power of 0.5. And this was proved by Cook and Haken from 1999 and by Pudlak. So putting it together, the share size in schemes using monotone formulas with slice functions is 2 to the power of omega of n to the d for some constant d, where d is at least 0.25. And the low bound holds even for not only monotone formulas, but also for monotone circuits. And I believe that the lower bound for monotone wheel formulas should be should be even possible exponential. Yes, Evgen.
But just to check, the theory is the low bound of Pudlak, etc. There exists a function. It could be that in the secret sharing schemes of the CDS function, the use is very different from this.
No, the function is the function describing the access structure.
Every monotone.
The
low bound is there exists a very particular.
So the function is the function we apply that is the function describing the access structure. So this is there exists a monotone access structure that requires long shares, and the CDS, the gates is any slice function or any any slice function, any CDS that you want to compute for any function.
I see. So it implies for any CDS.
Yes.
Not just
Without any restriction, which function you apply, the CDS and what protocol you apply, what CDS protocol you apply. So you have to be very cautious about this limitation. It says that if you use a monotone formula as is without any other tweaks, the size of the shares will be exponential. I don't know if you can use a simple tweak to bypass this lower bound. It's possible, and I don't know, and it's possible that you can do something much better.
I don't understand something. The slice function, is that part of the access structure or part
No.
of the methodology that you are in the lower boundary?
I'm saying that the few constructions we have now for secret chain schemes construct a monotone formula with slice functions.
There exists some access structure.
For every access structure,
Yeah.
they construct a different formula with slice functions as the gates.
I see. The gates are, even if the original access structure is not a slice function.
No. For every access structure, not a slice function. Any how much? That's the time left. Oh, I really won't get to the upper bounds. So I'm saying that for every access structure, they construct a formula with slice function as its gates.
And you show there exists an access structure for which that technique would yield.
Yes. It's a weakly exponential. What?
I mean, this is far from the upper bounds that we have, right?
This is upper bound, but I'm not sure if they exist. But I said this low bounds hold for monotone circuits even, and I not sure if there exist better low bounds for monotone formulas, and I believe that even if they don't exist, it should hold. I'm saying that, yes.
Is this generalization to real formula necessary? If I just want the monotone Boolean formula, then is there a gap or in the theorem that you...
Again, I don't,
So your theorem says every monotone formula with slice functions of say things implies a monotone real formula. If I just want the monotone formula,
it can be
it can be much larger.
It can be much larger. We know that there are secret chain schemes that exist for functions that have a large monotone formula. So yes, it's necessary. Okay. So let's go quickly about the other law bounds. So important class of secret chain schemes that until recently was included nearly all secret chain schemes are linear secret chain schemes. So a secret chain scheme is linear over the finite field FQ if the shares are generated as a linear function. Specifically, the scheme, we have a secret which is one element of the field, and the dealer chooses the random elements from the field, and it chooses each element independently with uniform distribution, and each share is a vector over the field, and each coordinate in this in the vector is a linear combination of the secret and the random bits. So let's see a simple example. In this case, the scheme will be over F17. I felt like having 17. And the dealer chooses two random elements in this field. The share of P1 is a vector of length 2. It's S plus R2 plus R3, and S plus 4R2 plus 6 in R3. And the shares of P2 and P3 are also linear combinations. And actually, this is an example of a Shamir scheme, writing Shamir scheme differently. So Shamir scheme and the Ito-Saito Nishizaki are linear schemes, and all schemes based on monotone span programs are linear. Okay. So notation will describe the scheme by matrix with M rows and L columns. So this describes the linear transformation of the scheme. And the size of the scheme is M, and the size of the shares is M log, the total size of the shares is M log Q. And a secret chain scheme is linear if it's linear over some finite field. What we know by counting arguments that for most access structures, gamma, the share size in every linear secret chain scheme over F2 realizing the access structure with one bit is omega of 2 to the n over 2. So it has to be exponential, and the exponent is at least n over 2 in linear schemes. So this is over F2. I want to go into the proof, but it holds for every field. So every linear secret chain scheme realizing the access structure, both access structures requires exponential size shares for sharing one bit. So this is a counting argument, simple counting argument. And we have even a stronger law bound, never published, that for most access structures, for every finite field FQ, the size of a share of every linear secret chain scheme realizing gamma over this field will be 2 to the power of n over 3, in this case, times the length of the secret. So this, you cannot use counting argument because the number of finite fields is infinite. And I would say only one thing about it. The idea of this proof is to use a new result about representable matroids. So without going to the definition of matroids, there's a doubly number of matroids, but the number of representable matroids is only exponential. It's 2 to the m over 3, and the m over 3 is what gives n over 3 in the low bound. So I won't go into the upper bound on the number of representable masquerade is 2 to the m to the power 3, and the lower bound we get is 2 to the power of n over 3. Because the 3 will correspond to n over 3. Okay.
So given an access structure, I can decide in finite time whether there exists a field for which it can be realized in smaller size, say? I don't have to go infinitely over all the time or something?
No, the result is existential. It counts number of number of fields, or actually you can probably do it in double exponential fields or something. Given for every n, there's a finite number of fields. And then you have to check over the wheels, which I'm not sure. Okay. Okay. So, so this was for implicit functions. There are also lower bounds for explicit functions. Until recently, the best lower bound for explicit access structure was quasi-polynomial, was 2 to the power of log squared n. So it's better than polynomial, but much less than exponential. And this lower bound actually holds for a stronger model, multilinear, where the secret can be a few elements over the field. So this is the best lower bound for multilinear. In recent work, it was improved for 2 to the power of omega of n times the length of the secret for an explicit function. So this was proved in a series of works. The last work by Pitassi and Robert. Previous works included other authors. Only one thing. In the first 2 papers, they claimed that they proved the lower bound for the secret sharing schemes. They didn't. Only in the last paper, they did it for secret sharing schemes. So, okay. Now I was supposed to go to upper bounds, and I won't go into upper bounds. The police wanted me to stop. So I only want to say that for the upper bound, there were the work of Tenren and Vinod used the reduction to CDS protocols. Our work and Benny and Oded's work defined a stronger notion of CDS, robust CDS, and using 2 different reductions, we proved the upper bound on secret sharing schemes. So, as I said, secret sharing schemes are fun. I've been doing research on this question for more than 30 years, for nearly 30 years. And I find this subject fascinating, and I hope that I managed to convey this to you.